Good morning, everyone. We're going to return to Chapter 8 this morning. So where we're at in the class, we're going to get through probably about the first half of Chapter 8 today. We will come close to finishing Chapter 8 on Monday, and then we'll be starting Chapter 9 probably by Wednesday. We're covering through Chapter 9 for midterm 4, which is in a couple of weeks from now. Okay, so the Born-Haber cycle is something that we use to actually calculate a lattice energy. So last time we were discussing that the lattice energy, which for something like NaCl, would be the energy for the reaction of sodium chloride forming its gaseous ions. So these in the gas phase. And that this lattice energy is a measure of how strong that ionic bond is. So we use lattice energies that give us an idea of how strong an ionic bond is. We'll go through what it means and the effect that we have on changing the charges of the ions in a moment, but you can probably imagine now that if we make the ion charges greater, like if we had calcium and oxygen, we have a 2 plus and a 2 minus, that would probably be better. You know that the higher the charge of the ions would probably be more strongly attracted, probably would mean more energy would be required to separate those ions from each other. And then likewise, we were getting into this at the very end of class on Wednesday, but if we make the ions smaller, that actually makes the interaction stronger. So if we make the ions closer together, then that's going to require more energy to separate the ions. But this slide here is showing us how we actually calculate a lattice energy because it's not a reaction that directly can occur. So there's no simple way just to like blow up sodium chloride into its gaseous ions. It takes so much energy, it's just not going to spontaneously take place. And so the way that energy value is calculated is through something we call the Born-Haber cycle. And the only thing that's maybe kind of interesting here is that this ends up being like a very big Hess's law cycle of equations. So if we start from sodium chloride and kind of address the question, can it form its elements? Or can we just think of the reaction where we take NaCl as our reactant, as a solid, and let's form Na solid and then Cl2 as a gas, because those are the natural states, those are the most stable states of sodium and chlorine at room temperature. This reaction here is the negative of the delta HF equation for sodium chloride. So this is the negative of the delta HF of sodium chloride. And it's negative because we just flipped that formation reaction. So instead of forming the compound, we have it as a reactant forming its elements and their standard states. Now, if you notice that this step here, going from sodium chloride to its elements, that requires the absorption of energy. I think that should make sense. If you think of it in the opposite way, if we took sodium and chlorine and want to form sodium chloride, it makes sense that that would be downhill in enthalpy, that's going to be negative release energy, release enthalpy, because our product's more stable. That's why sodium chloride is more commonly found in nature than sodium or chlorine. In fact, we don't find mines of sodium. We don't find chlorine naturally on Earth. We only find sodium chloride because the sodium and chlorine are so reactive with each other that we're all essentially over here. And so if we're just saying energetically how much energy does it take to go to the elements, it's just the negative of the delta HF of sodium chloride. We could look that up in like the back of our textbook if we wanted to. And then we can also then say, well, what if you take sodium as a solid to a gas? So the only thing changing here is going from the solid sodium to gaseous sodium. So that reaction here, let me write this. Let me line up my reaction arrows. So if we have sodium solid to sodium gas, then if we're doing like a Hess's law summation, then we'd just be canceling out the sodium solid because it's now on the reactant and product side. And I've just changed the physical state of sodium into the gaseous state. This equation here, there's two kind of ways I can think of this delta H here. This delta H here would be the delta HF of the sodium gas, because sodium solid's delta HF is 0. So the delta H of this reaction is just dependent on whatever the delta HF is for sodium gas. We could look that up in a textbook as well. This is also the delta H of sublimation of sodium. So it's the enthalpy of sublimation of sodium solid. For a phase change, for anything to go from solid to gas, you could think, does the solid have to absorb energy or give energy off to go from solid to gas? And it's the same thought as going solid to liquid. Remember, melting requires the absorption of energy. Boiling requires the absorption of energy. So direct solid to gas requires the absorption of energy. These delta H's here all have to be greater than 0. So in other words, we require more energy to be absorbed to go from sodium solid to sodium gas. If we then want to break the bond in chlorine and Cl2 to form chlorine atom, when I write this reaction here, a half Cl2. Now let's interpret this, because sometimes it's hard to interpret half a molecule of chlorine, because that maybe doesn't make sense, but can we interpret half a mole of chlorine? So I think that does make sense. So a half a mole of Cl2 would be 3 times 10 to the 23 molecules of Cl2. So if we're thinking on the mole level, and think about these coefficients as being moles, and I think it makes sense what half a mole would look like. We're going to turn that into a mole of chlorine atoms. So let's convert that from Cl2. So half a mole of 2 chlorines bonded together. Let's break the bond and form chlorine atom. And so this is our bond energy. So this equation here is the bond energy is Cl2, or it's the delta HF of Cl. So those two different sort of ideas, we can think, what's the enthalpy of formation of Cl? Cl2 is 0, but Cl, we could look it up in a textbook. We could look up a bond enthalpy of chlorine, and this would be 1/2 of that bond energy since we have half a mole. So there's a few different ways we can think of this step here, also requiring the absorption of energy. So the delta H of these steps here, greater than 0, energy has to be absorbed. So if we're taking sodium chloride from the compound to its elements, requires energy to be absorbed. To go from sodium solid to gas requires more energy. To go to go from Cl2 to Cl requires more energy to be absorbed to break that bond. And then we need to start ionizing. So let's ionize sodium first, lose an electron off of sodium. So let's go from sodium gas to sodium plus, still as a gas. Now our ionization energies and electron affinities from the previous chapter, in chapter 7, those are all for gaseous elements. We mentioned that then, and the reason why is because if you want to compare the ionization energy of sodium to chlorine, where chlorine's a gas, sodium's a solid, you don't want the delta HF of sodium solid to gas appearing in that equation. You just want to know what's the difference of the ionization energy of the element of sodium versus chlorine, so we go gaseous elements so that we're not comparing their phase differences as well. But this difference of energy here, where we're losing an electron, this is the I1 of sodium. And so that required energy, if you recall, I recall that number, it's like 496. It's about 500 kJs per mole to go from sodium to sodium plus to ionize that electron. And then this is kind of where, if you recall, I was talking about, if you just go from sodium to sodium plus and then to Cl minus, that doesn't fully tell you why sodium plus forms and why Cl minus forms. It's not because those two events in and of themselves are energy beneficial. It's because once you make the ions, once you make Na plus and Cl minus, they then have that attractive force between each other. Okay, so when we take the electron off of sodium and then we add that electron onto the chlorine atom, we go downhill in energy to form Cl minus. So that's our electron affinity of Cl. And then the electron affinity of chlorine, this is the only one here that has a delta H that's less than 0, that's exothermic. So the only exothermic step here, let me go highlighter, is this step here. So that's the only exothermic step in this whole process. And all the other steps are endothermic, require the absorption of energy. Okay, so obviously the I1 of sodium, this is greater than 0. It takes energy to ionize, to remove an electron from any element. So all ionization energies were positive. Most electron affinities were negative. And now if we imagine adding all these equations up, I'm just canceling out what's on both sides, our electrons on both sides. And so the only substances that are not on both sides of the equation are sodium chloride. Let me change to a different color here. So sodium chloride, sodium plus, and Cl minus. So that's what this whole set of equations here would simplify down to. So now if we were to look up all these individual values, which we could do, it's kind of boring, it's really not the point. But if you were to look up the delta HF, the delta HF of sodium, chlorine, the ionization energies, electron affinities, add them in, then what you get in return, if we sum all of those up, we sum all these delta H's up here, we're going to get the net summation to the delta H being sodium chloride solid, forming sodium plus gas plus Cl minus gas. And then for sodium chloride, that ends up being about 800 kJs per mole in that ballpark. So a really strong attractive force between the chloride and the sodium ion. So this here is the attractive force between those ions once they're formed. Okay, so a long-winded process to just kind of show you that the Born-Haber cycle is just a mathematical way that we use something like Hess's law to go through a series of reactions to sum them up to determine a lattice energy. Now, in the old days, we would throw you a bunch of data and have you calculate it. To be honest, I think that's kind of boring. I mean, to me, the whole point of this process is just to see that you can determine through other experiments the delta HFs of different substances. You can determine ionization energies, electron affinities, and you can take those, sum them up in this process here, and ultimately get at your lattice energy equation down here. So the whole idea is like that's how we're calculating lattice energies, is through this sort of cycle of equations of other experiments and experimental values that we are able to know. And so this is just how we get the delta H of this reaction here, and we set that equal to the lattice energy. Again, I don't know why things spontaneously disappear when I don't even do anything on my screen. But anyway, so that's how we calculate lattice energies for different compounds. And so then when we go through the process of doing that for sodium chloride, 788 kJs per mole. But now what we really hope that we can understand is, well, what if you change the size of the ions? If you keep chloride the same and you change to lithium, notice that the lattice energy goes up. So if you're trying to separate lithium chloride, so the lattice energy for lithium chloride would of course just be the lithium chloride as a solid going to lithium plus chloride. The only difference here between sodium is lithium is smaller. And if you think of the equation kappa Q1, Q2 divided by D, so if we're thinking of how our charges are related to each other by their distance of separation, that as the distance of separation becomes closer together and that distance shortens, our energy of electrostatic attraction, this magnitude, is going to increase. So put two like charged particles, a plus and a minus, put them closer together, harder to separate. I think this makes a lot of sense. Imagine a plus and a minus 2 miles away from each other. There's no attractive force, is there? If the plus and the minus charges are so far away, they can't experience the attractive force. But if they're very close together, it's going to be harder to separate. Even closer, even harder. And so then you can see that if you go to potassium, which is bigger than sodium, so just think of how as you go from lithium to sodium to potassium to rubidium, as we're going from top to bottom, we're increasing in size. As we go down, we increase in size of those ions. And so as you go to a larger ion, you're just putting the charges further away from each other, weakening the attractive force. And then the same thing happens if you change the size of chloride, keep sodium the same, make fluoride smaller than chloride, so then that has a greater lattice energy, go all the way to iodide, the lowest lattice energy. And so we can summarize that here and see a few more examples. So that lattice energy is the energy associated with the conversion of ionic compounds into their gaseous ions. The idea here is it gives us a measure of that, or a relationship to the ionic bond strength. And so as we go to smaller ions, and those distances are closer together, we get a stronger force of attraction. But then you can also imagine if we change the charge magnitudes, if you make the charges bigger, now of course you can think the magnitudes of charge, or you could so let's make sure we think of -2 charge being greater in charge than -1 charge. And so think of the magnitude of that charge going from a 1 to a 2 is going to increase the magnitude of the charge. And so if you look at the lattice energies of things like Mg2 plus, O2 minus, calcium 2 plus, O2 minus, strontium 2 plus, O2 minus, that these lattice energies are about a factor of 4 higher than the +1, -1s. And so the charge magnitude has a big impact on lattice energy. And it's really, if you imagine doubling both +1 and -1's charges, you're sort of quadrupling the lattice energy because you've quadrupled the net charges relative to each other. And so then if you go in between, if you go a +2 and a -1, then those lattice energies are kind of in the middle. So the lattice energy of something like magnesium chloride, which has a +2, -1, so we get a stronger bond as a result of having a +2 charge with a minus, and we actually get 2 bonds that we're breaking. If we break magnesium chloride, we're getting magnesium 2 plus and then 2 chloride ions. So the lattice energy is the separation of that compound into its now 3 ions because of the formula of those compounds gives us 3 different ions. Then we get lattice energies that are a lot higher. But then notice that if you go from magnesium chloride to a larger strontium 2 plus ion, that you decrease the lattice energy due to the size trend. So you can see this trend here is due to the increasing size of the cation, and increasing size will weaken the lattice energy, weaken that attractive force. And we can see that as well for the trend for these guys here, that as you go from magnesium to calcium to strontium, you're going to a larger ion as you go down those three here. And so we weaken that lattice energy as a result. So we're lowering our lattice energy as we go down into a larger 2+ cation. And if you go all the way to a 3+, 3-, so scandium nitride is SCN, ends at 3- ion. There's not a lot of compounds that have a nitride ion that's truly ionic, but this compound's one of them. Look at that lattice energy. It's about a factor of 9 higher than those compounds that were about 800 or so kJs per mole when they were +1, -1. Go all the way to +3, -3. We're about a factor of 9 higher because we've now taken those charge magnitudes from +1, -1 to +3, -3. So we've increased those charges by about a factor of 9 and have a much higher lattice energy. So lattice energies increase with charge by a large amount, and then the size trend has a relatively smaller impact, but still a marked impact on changing the lattice energies where we want the ions to be smaller. Remember, when we're talking about charge being shared, being smaller is usually going to be better for the charge to be shared more effectively, therefore to require more energy to separate those compounds into their ions. Let me take a detour here to do a demo that kind of relates to something from chapter 7. And so what I want to compare here or discuss before we think about our demo is if we were looking at compounds that are sort of like manganese sulfate to iron sulfate. There's 4 compounds we're going to look at today: nickel sulfate and then zinc sulfate. The question is, can I think for these compounds here, what are the sort of electron configurations for the cations? So all of these have a 2+ cation, because we know, of course, sulfate's a 2-. And so we're sort of comparing manganese 2+, iron 2+, nickel 2+, and zinc 2+, and trying to think, well, what's their electron configurations? And so if we're looking at manganese, remember we might start with manganese 0 before we think about 2+. And so when we're doing a cation configuration, if you forget from last time, it's probably better to start from the uncharged elements electron configuration. So for manganese, it's going to be a 4s2, so it'll be argon configuration, followed by a 4s2, and then we're across the D subshell. If we count across the manganese, 1, 2, 3, 4, 5 across. And then we can do an electron diagram. And so our electron diagram would, let's actually then think of manganese 2+. So let's take our manganese 0 now and then remove the 2 electrons that go to the 2+ charge. And so the electrons we're going to remove are not the last 2 that we put in, but they're the largest 2 electrons. Because the larger, the n=4 shell is larger than the whole n=3 shell. So it's going to be easier to remove the n=4 electrons, those 4s electrons. So we remove those first and make the configuration for manganese as that 3d5 configuration as the rule. So we lose the electrons first from the highest n with the highest L. So that's the order that we lose electrons in. This is just a fancy way of saying largest. So as n goes up, the size of the orbital goes up. And as the L goes up too, this size goes up. So if you're comparing a 4s to a 4p, the 4p would be bigger than the 4s. But if you're comparing a 3d to a 4s, the 4s is bigger. So 3d is in the n=3 shell, 4s is in the larger shell. So we lose the largest electrons first, and then our diagram should show our configuration for a 3d5, 5-spin unpaired electrons. Now, there's something really interesting with spin unpaired electrons. We call, like if we think of the magnetic trend or the magnetic effect, I got a screen here. So if we think about the magnetism of that compound or that sample, we would call this something that we give the term paramagnetic. So paramagnetic, what this means is it means it's drawn into a magnetic field. And so now if you think magnetic versus non-magnetic in terms of permanent magnets, that's kind of a different thing. So a permanent magnet is something that has a built-in dipole where the dipoles in the metal like align with each other, so it's permanently, so the substance has a permanent charge. That's something different than what we're talking about here. What we're talking about here, if you have a sample of manganese sulfate, each of the metal atoms has a net spin because of these unpaired electrons. So anytime we have one or more unpaired electrons, there's like a net spin on that metal ion. But then if you think of a sample of nickel sulfate, all those metals are pointing in random directions. So none of those directions are like aligned in any specific direction. To have a permanent magnet just would align all those dipoles in the same direction so they're always aligned. So a permanent magnet has its dipoles always aligned. Our sample just has its metal atoms in whatever orientation they happen to be. But if I put a magnetic field near it, those metal atoms are going to align towards the field. So the effect that I should have here for nickel sulfate, or excuse me, for manganese sulfate, is if I take a magnetic wand, I should be able to see that it's drawn into the field. And so that's the effect of paramagnetism. That's it being drawn into the magnetic field. And so we can see that for manganese sulfate, 5 unpaired electrons. Now we can see the trend for iron sulfate too, because if I look at iron sulfate, the Fe0 would be a argon 4s2, 3d6. And so if we're going to the 2+, I again remove the 4s electrons. So I have a 3d6 configuration, so 5 spin up. I spin pair 1, so I have 4 that are spin down. And so now if I take my magnetic wand to this, I should see the effect. It might be a little bit less than the previous salt, but it's still being drawn in towards the magnetic field. And so now let's look at nickel. Nickel should still have unpaired electrons for nickel 0. That would be argon 4s2, 3d8. And now even if you thought it might be a 3d10, which it's not, nickel's not one of the metals that has an anomalous configuration, but even if you did think it was a 3d10, and you weren't entirely sure if this was one of those weird anomalous elements, we're going to either kick away the 4s2, or if you thought it was a 3d10, you would have removed 2 of those 3d electrons to go to 3d8. So in any case, you're going to arrive at hopefully a configuration that has 5 spin up and then 3 spin down to give us 8 total. So I only have 2 unpaired electrons, but I should still have a net trend here. So all 3 of these are paramagnetic and should be drawn into a magnetic field, maybe not as strongly. So the effect is, it looks probably pretty similar to the manganese, but the manganese, I can get it moving a little bit more because it's more strongly drawn into the magnetic field than this sample here, which is the nickel sulfate. So then the last case is zinc, and so zinc is different than the other 3. Zinc 0, of course, would be argon 4s2, 3d10, so remove the 4s. And so then we have all 10 of our d electrons spin paired. It's probably pretty obvious, but the argon configuration is all spin paired. So if we have a noble gas configuration, those are all spin up, spin down paired electrons. So for zinc sulfate, all my electrons are spin paired. We call this diamagnetic. So instead of paramagnetic, or excuse me, something that's diamagnetic, instead of it being completely unaffected by a magnetic field, it's actually weakly repelled by a magnetic field. I'm not sure if we're going to see that trend here, but because it's so weak, we may not actually be able to see it. But we should either see no effect, or if anything, we put the magnet and it moves a little bit away. That would be generally what we see for diamagnetic substances. So let's compare and see what we get here. And this sample here is the zinc sulfate. I can almost see it being drawn away instead of, if I look at this one here, like the sample, see how it's coming towards the field until I lose enough pull to pull it in. So it's being drawn towards the field. This one here, it's really hard to see, but I can kind of pick up a little bit of a repulsion away. It's not moving towards it. It's almost like when I get close, it's moving a little bit away. But it's really weak, so it doesn't really push it away that hard, so it's pretty hard to see. But this is the effect of diamagnetism when we have all of our electrons spin paired. So all spin paired electrons, diamagnetic. One or more unpaired electrons in that substance would be called paramagnetic and would be pulled into a magnetic field. Now we're going to see this again in chapter 9 when we in particular talk about oxygen. Molecular oxygen, O2 that we breathe in, is actually really weird in that it has unpaired electrons. So we're going to have to try to figure out why that's the case as we get through kind of Lewis structures and into some molecular bonding theories. So we'll come back to paramagnetic objects when we get back into the later parts of chapter 9. Okay, so I just wanted to do that here to kind of compare what it means to have unpaired electrons. So when we are talking about different, cation configurations, if they have spin unpaired electrons or not, there's a big impact on if they do or they don't. And sometimes it's important to see why we kind of stress that question. Okay, so just remember for cation configurations, you always remove from the largest orbitals first, the highest n with the highest L, and that's not always going to be the same order you filled the electrons into those orbitals. Okay, so let me take... Okay, so now let's come towards, so if the goal of chapter 8 was to understand ionic bonding and covalent bonding, the ionic bonding was just simply a nature of trying to understand what a lattice energy is. We understand that hopefully from just the idea of separating ions, also then calculating it from maybe something like a Born-Haber cycle. I don't expect you to necessarily replicate a Born-Haber cycle, but I think what's important to recognize is it was only the electron affinity of the anion that went downhill in energy was exothermic, and then the lattice energy itself, if you think of taking cations and forming the compound, that's exothermic. If you think of then once you have the compound and separating the ions, of course, that's endothermic. And so the only natures of the interactions in that Born-Haber cycle that were attractive in nature are the electron onto chlorine, and then the plus and minus, once they're formed, being attracted together, being the main driving force for why those compounds are forming kind of in the first place. Okay, and so then we're measuring ionic bond strengths as a virtue of charges and sizes of the ions. Now, when we get into the non-metallic elements and some of their bonding trends, we have to talk about a different type of bonding, that being the covalent bond. And so covalent bonds, if we're picturing maybe something like an H atom over here, each one has an electron that's being shared across the two nuclei. This is kind of what we mean by the sharing of electrons. So this might be the bond that we're thinking between H2 atoms. And so when I start to draw this line here, that this is the sharing of two electrons. So two electrons being shared, shown with the line. If I showed a double bond between, say, oxygen having a double bond, this is 4 electrons being shared. Triple bonds, like between nitrogen, would have 6 electrons being shared. And so, probably know this already, but that's the difference between single, double, and triple, is just as we go and change the type of bond, we're just sharing more electrons between the nuclei. But for the H2 bond, to kind of look at this bond here, this diagram here is kind of showing us a bond diagram of kind of showing us where if you had your 2 hydrogen atoms at far separations, if you have 2 H atoms that are really far away from each other, no attractive force between them, start bringing them closer together, they're eventually going to form a bond. They form a stable bond that has some bond distance that's best for that molecule, H2 around 0.74 angstrom. Not worth memorizing that number, but if you push past that value, the energy goes up. So all bonds are going to have like an ideal bond distance, and this kind of goes the same thing too, though we didn't really talk about it with like NaCl, lithium chloride. As you go to a smaller ion, the bond length shortening. As you go to a bigger cation, the bond length's increasing. So you can look at the bond distance even for ionic compounds. The 2 nuclei, of course, are not directly on top of each other in ionic compounds, and certainly not either with covalent compounds. And so we reach an ideal distance here of about 0.74 angstrom for H2 in terms of its ideal bond distance. And so this bond diagram here is also showing us that this difference of energy to go from here to here, so the energy it takes to go up, is that bond energy. So this is equal to the bond energy of H2. If you recall from chapter 8, chapter 5, when we talked about bond strengths, we can quantify this. That's about 436 kJs per mole of H2. And so that's the energy it takes to go from H2 to 2 H atoms, is our bond strength of H2. And so of course it takes energy to separate the bond, and about 430 some kJs per mole for H2. If you look at bond strengths for covalent bonds, like we'll summarize some bond strengths towards the end of chapter 8. Again, we summarize them in chapter 5 as well. But bond strengths for covalent bonds are usually in the 200 to like 800 range. So a little bit weaker in terms of bond strengths compared to the ionic compounds. So in terms of sharing charge, if we have a plus and a minus, that's usually going to be a stronger attractive force than a covalent bond. So covalent bonds generally a little bit weaker than their counterpart ionic bonds. And so then if the goal is to try to come up with, well, what kind of Lewis structure would we write for two different, for a molecule, how could we come up with these? Well, you might look at hydrogen, how each hydrogen has like one electron. And so if each of the atoms can share their one electron with each other, then they would obtain that noble gas configuration like helium has, where helium has 2 electrons. So each hydrogen kind of gets the benefit here of having 2 electrons closest towards it through the sharing of electrons is kind of the idea. And then for one to go to plus and the other go to minus just doesn't work. So if you think, why does H2 not just go to H plus and H minus? Well, if you recall, the ionization energy of hydrogen is way too high. The ionization energy of sodium is like 500, hydrogen's like 1300. It's way too high for hydrogen to lose an electron, and there's not much energy benefit for the other hydrogen to accept the electron. So it's going to be happiest for these atoms. On the nonmetallic side, we're going to see mostly compounds with H, carbon, nitrogen, oxygen, fluorine. These are compounds that don't have a low enough ionization energy in any of those atoms to form cations like we do on our ionic compound side. For Cl2, if I'm picturing 2 chlorine atoms, I can maybe think from like a Lewis dot diagram perspective that each chlorine has 7 valence electrons. So this is a 3s2, 3p5 outer configuration, just showing us that we have 7 valence electrons. And then the other chlorine can kind of look the same. And then we can share their, if you will, odd electrons. So they're each kind of deficient of that noble gas configuration by 1 electron each. So if they make a single bond, then if you notice each chlorine now has 8 electrons closest to it. So if you think, sometimes we call this the octet rule because we see for things other than hydrogen and helium that they tend to form with 8 valence electrons surrounding them, either through forming ions in ionic compounds or in the case here of sharing electrons through covalent bonding. If you look at fluorine being a 2s2, kind of like chlorine configuration, having 7 valence electrons, but a 2s2 configuration, just trying to make sure we see that it has 7 valence electrons, so that's why I write 7 dots. Hydrogen has 1, and so then we can share a single bond. So now fluorine has 8 electrons closest to it, hydrogen has 2, and so we're sharing electrons coming up with that stable count for each of the atoms having kind of that noble gas count. Water, we can have H2O from oxygen having a 2s2, 2p4 configuration, so that's 6 valence electrons. So if I'm counting valence electrons, 6 valence electrons for oxygen, of course 1 valence electron for hydrogen. For each of the hydrogens, so we just have hydrogen pair up here, hydrogen pair up here to have our bond between water, having 2 single bonds between H and O. A Lewis structure is going to really try to help us try to figure out, should we have single bonds, double bonds, or triple bonds between the atoms? And then are there other things we need to consider? We'll see some more complicated trends like resonance. We'll see some cases where we break the octet rule as we continue with some Lewis structures. But for a lot of our simpler Lewis structures, for things like water, things like H2, for molecules that are relatively simple and probably things you've seen before, we can pretty easily sketch a Lewis structure just from coming to like a dot diagram for like nitrogen, 5 valence electrons. So I start with nitrogen with 5, hydrogen pairs up accordingly with each of its valence electrons to make the structure for NH3, 3 single bonds. CH4 has 4 valence electrons for carbon, so carbon with 4 valence electrons, hydrogen with 1 each. Pairs up and makes for 4 single bonds for CH4. What about O2 and N2? Well, let's just think about O2 first. So if we have a configuration of O2 that looks something like this, the other oxygen similar. And what I'm just drawing is each oxygen with 6 valence electrons. And so now if I just share one bond, then they each still don't have an octet. Each oxygen only has closest to it, in that case, 7 electrons. So what if we share a second set of electrons to make a double bond? So O2 goes double so that we're sharing these electrons to make the double bond. So we have 8 electrons around each of the oxygen atoms with a double bond. And then nitrogen. And the only thing is, if you're not sure why I'm drawing the particular dots around the atoms to start with, it's just the valence count. This is just from looking at nitrogen on the periodic table, realizing that each nitrogen should have 5 valence electrons. And if I wanted to add an electron or take one away from nitrogen, I have to change its charge. I would have like N2 plus or N2 minus or some other formula. But if I have N2 neutral, each nitrogen brings forth its own electrons. The other nitrogen has its own electrons. And it's the outermost. It's always going to be the valence electrons that are the most important. I don't need to worry about the core electrons. They're really close to each of their nuclei. They're not really involved in bonding. And so if I'm going to pair up nitrogen's electrons, I go ahead and pair up all 3 sets of their unpaired electrons and come up with a triple bond. And so that's why nitrogen, we write it as a triple bond, so that each nitrogen has 8 electrons. Now, will every compound exist following this octet rule? No, we're going to have octet rule violations. We'll try to understand why we have some stable compounds that violate the octet rule. But for these compounds here, they're all satisfying the octet rule, with the exception maybe of hydrogen, which you can say hydrogen only has 2, but it's really more of a like noble gas configuration rule than an octet rule. Yeah.
For nitrogen having 5 valence electrons and they're sharing 3 of them, does it matter like which subshell that they're sharing in, like the 2s and 2p?
Oh yeah, I would probably say that gets a little bit more into like a bonding model we'll come back to later to try to piece together, well, what do those really look like? Like how are we really overlapping? If you think of unpaired electrons being in like p orbitals, versus like s orbitals, that does matter. We'll talk about MO theory towards the end of chapter 9 to help us understand like how and what might actually be going on at kind of like an orbital level for something like N2. But for now, I think just try to think of just like trying to get the net bond order, the bond type as single, double, triple, and not worrying yet about like, well, how does this actually happen? We'll get into some of those aspects later. That's a really good question though. One other thought that we'll start to calculate a lot is something called formal charge. And formal charge will help us try to see is some atom like building up charge relative to another atom in the formula. And let me just do a couple on here. Let's maybe focus on the middle, water, ammonia, and CH4 for a minute. And so when I go to calculate the formal charge is I look at oxygen and I count the electrons closest to it when I make my bonds. And I'm going to assume, or I'm just going to, for the calculation of the charge, I'm going to break my bonds in half. Okay, I'm breaking the bonds in half just to calculate the net charge on the one atom versus another. And so I'm going to calculate the charge on H, and then I'm going to calculate the charge on O. Now, the formula for formal charge, it's one of the summarized equations in the back of the chapter 8 in the book. It's the valence count for an atom, and then minus all of its non-bonding electrons, and then minus half of its bonding electrons. And so if I'm just doing this in terms of like the box, it's like the first key is I take the valence count of 6 and I subtract 1, 2, 3, 4, 5, 6. I'll write the equation in just a minute. But to me, the equation is not so useful. To me, what's useful is like box the atom. By boxing the atom, you break the bonds in half by result of sort of building the box around the atom. So you keep the non-bonding electrons on the atom they're attached to, and then you break the bonding electrons in half. And so the net charge on oxygen is 0. So there's no charge on oxygen. Hydrogen's 1 minus 1, it's also 0. And so something you're gonna see a lot, and not all compounds, but in like the really, really stable compounds, you're almost always going to see that you have 0 formal charges across all the atoms, especially when the molecule is uncharged. Again, not always going to be the case, but you're going to see this a lot for things like NH3. Nitrogen should have 5 electrons closest to it, and if we look at nitrogen, we have 1, 2, 3, 4, 5 electrons closest to it. So just break the bonds between nitrogen and hydrogen in half, put one of the electrons closest to H, put the other electron closest to the N. So this is kind of the idea. If the bond's perfectly like 100% covalent shared electrons, by sharing electrons, half's probably closer to one atom, the other half closer to the other. Now, if you think of oxygen O2 this way, you're just breaking the bonds in half. And so each oxygen still has 6 electrons closest to it. So these atoms both are neutral charged. Usually in Lewis structures, I'm not worried about showing 0 formal charges. So usually in a Lewis structure, I'm not going to take the time to show or to write the zeros, but we can do it now just to make sure that we see for nitrogen. It should be 5 for each of the ends, and then each end has 5 electrons closest to it. And so 5 minus 5 for neutral for nitrogen, and then carbon should have 4 electrons closest to it, and then it does have 4 electrons closest to it. I just have to break the bonds in half to see it. And so the formal charge of carbon is 0 in this molecule here. So let me zoom out a little and write the formula for formal charge if you want to see a way of expressing this out. The formal charge is the valence count for an atom minus the non-bonding electrons and then minus 1/2 of the bonding electrons. Now, if we go back through, let's go back through CH4. Like if I'm calculating, say, for hydrogen. So hydrogen's valence count is 1. And then it has 0 non-bonding electrons. And then this bonding pair of electrons here, there's 2 electrons there. So if you're not drawing the box and you're using the equation, then you go 1/2 times the 2 bonding pair electrons. These are the 2 bonding electrons. And then, so that would be 1 minus 1. And so that would equal 0 for hydrogen. So just like all the charges in an IC add up to the overall charge of the compound, just like all of the, in chapter 4, all of the oxidation numbers, if we sum up all the oxidation numbers, they have to add up to the charge of the molecular ion. So too do the formal charges. So if we sum up all the formal charges, they need to sum up to the charge of the molecule. So in CH4, and all these molecules on this page, they all have 0 formal charges on every atom, and you add 0 up across the molecule. Of course, the molecules are uncharged. And so the molecules are uncharged, all the formal charges were uncharged, so that kind of checks out. Now, this equation here, I'm usually just drawing the box. So I usually don't come back to this equation too much. I'm usually just trying to picture the structure, draw a box, try to calculate the charges. Okay, so now how do we do Lewis structures for some other molecules like CO2? And we're actually going to come up with a comprehensive set of rules for sketching a Lewis structure. And for some molecules that are on the really simple side, like i.e. the ones on the previous page, like for things like water, you may have known the Lewis structure coming in the room. You may have already known what that Lewis structure looked like. You may have already known what CH4 looked like. We've sketched CH4's Lewis structure even back when we were talking about naming the compounds. So you may have kind of been like, well, CH4 probably looks like 4 single bonds. So some Lewis structures you may know. Some you may be able to simply come up from like a dot diagram. For like CO2, one way to come up with that Lewis structure is just to kind of picture the bond, how do we get to something that shares electrons and gives us an octet on both sides. Let me actually do this second oxygen a little bit different. Let me put the unpaired electron here and here so I can pair up the unpaired electrons of carbon. So I can make a bond here, a bond here. So I'll make like 2 bonds on either side. And so that's through a dot diagram how I could get to the double bond of carbon. So I just kind of want to make a bond using all 4 of the electrons of carbon. I don't want to use the same electron of carbon to make 2 different bonds. I want to use the different electrons, all 4 of the electrons, to make the total of 4 bonds around CO2. So I end up with CO2 with 2 double bonds. And so that's our Lewis structure of CO2. You may have known that Lewis structure as well. You may have, if I just said, what does CO2 look like? You may have said, well, I know it has double bonds. Maybe you forgot why. One of the ways you can remember why is just that's how the dot diagram kind of balances out the electrons. In terms of the charges here, break the bond in half. Oxygen's still 6 minus 6 for oxygen. And then carbon, 4 electrons is its valence count, and it has 4 electrons closest to it. So 4 minus 4 is also 0. So 0 across the board for CO2. Now, something you'll see a lot in this chapter is kind of comparing bond lengths will come up a fair bit because we can compare single bond lengths. If two molecules have single bonds across it, we can use our atomic radii bond trend, the bond size of atoms from chapter 7. So if I'm comparing left to right, size becomes smaller as we go left to right. So if I'm comparing two different molecules that have single bonds, we can compare their bond distances from like a chapter 7, just relative atomic radii size comparison. We'll make some trends like that later on as we continue. But then if I'm comparing single versus double versus triple, we can make a comparison right off the bat. If you look at nitrogen-nitrogen with a triple bond, N2 does this. It has a really short bond. If we add a hydrogen onto either side of nitrogen to make a different molecule, it has a double bond instead of a triple. And that bond distance is greater because we now have fewer bonding electrons. So instead of having 6 bonding electrons, we now only have 4 bonding electrons. And those bonding electrons are the glue that are holding the positively charged nuclei together. These electrons are what are bringing, let me use a different color. These are what are bringing the nuclei of nitrogen closer together. So the positive charge is being pulled in by the extra bonding electrons to be shorter for N2, longer in the case of N2. If we add 2 hydrogens, I'm just trying to show you a molecule that would have a single bond for nitrogen. There's no way to take N2 from triple to double to single just as nitrogen. Nitrogen is a triple bond between the two. So I have to have a different compound to give me a nitrogen with a double bond. Then if I have a different compound where nitrogen has a single bond, so don't worry about why this molecule has a single bond yet. Just worry more about if it had a single bond between 2 ends, that bond distance is even greater. So now only having 2 electrons between the nuclei of nitrogen serves to increase the bond length. So we can also just kind of compare and see, and this becomes almost like a check. Like when you think something has double bonds or single bonds, you should be able to predict that double bonds should be shorter than if the structure had single bonds. So for like CO2, we don't see the comparison here, but the carbon bond distance is really short. If it were really some kind of single bond, the bond distance would have been greater. So you can compare bond length trends, and it kind of helps support and give some validation maybe to the structures that we come up with. So when we were calculating formal charge, we were assuming the bonding pair electrons were equally shared, but we don't always have an equal sharing of electrons and bonds. And so we can have a bond that's polar or a bond that's nonpolar. And so a nonpolar bond, the electrons are equally shared. And then a polar bond, one of the atoms is more pulling the electrons in that bonding pair closer towards itself and has a greater force for those electrons. And so 2 quick comparisons of compounds that have an equal share, one would be Cl2, so chlorine. If you have the exact same nuclei, kind of think you have the electrons here, which are both negatively charged. Does one of the 2 nuclei win the tug of war trying to pull the electrons more closely towards itself? Well, Cl2 has 2 equally strong nuclei, or 2 equal nuclei, and neither one's going to beat out the other in terms of pulling the electrons towards itself. So you can think one of the chlorines tries to pull the electrons, the other pulls the electrons, and then they balance each other out. So there's no net pull, so this molecule here is perfectly nonpolar, and each of the atoms is truly 0 charged as a result. If we compare swapping one of those chlorines out with a hydrogen, have HCl instead of Cl2, then now we have our 2 electrons here, and we can think, well, which nuclei wins the pull? So chlorine's going to try to pull electrons towards itself. So too is the hydrogen, but chlorine benefits by being more positively charged. If you think of the relative electron affinity, think about the relative size of chlorine. So think about how chlorine is going to be pulling electrons towards itself because it has a more high effective nuclear charge. So the effective nuclear charge as we go from left to right is increasing. It even increases as we go from top to bottom. So if we think of the Z effective, the effective nuclear charge of chlorine, it's a lot greater than that of hydrogen. And that's going to allow chlorine to pull those negatively charged electrons more closely towards itself. So what would be the impact if these 2 electrons here were more like one of them's here and the other one's here, closer towards chlorine on average, not closer towards hydrogen? Do you think that's going to make chlorine more negative or more positive in charge? So we're putting more electrons that are negative closer towards that nuclei, And so that's going to make this carbon, or the chlorine here more negative. So it makes that partial negative, and then makes the hydrogen partial positive, where the delta sign just means partial. And by partial, well, let's think about what we would mean by full. If it weren't partial, if it were full, it would have been H plus Cl minus. So this would be if it went ionic. So full is +1 -1. And so partial is somewhere between 0, which is nonpolar, and somewhere, between about maybe 1/10 to 2/10 to 3/10 of a charge. We can actually calculate that charge. I think I'm going to save that calculation for next time because I want to try to talk about one other thing before we leave. I will allude to the fact that, well, one, you can see the charge distribution through these kinds of diagrams. So if you look at a diagram like this, if you're comparing HF has the same trend as HCl. You're noticing that this atom here is picking up a different charge than this atom here. And so you're coming up with like a plus minus here for HF. You didn't for F2, just like you didn't for Cl2. So no charge here, so this is nonpolar. This is polar. And then if you get all the way to LIF, well, that's ionic. So that's like +1 -1. But if you notice, there's not too much of a difference between what the plus and the minus look like for HF versus LIF. But HF doesn't quite get fully to the +1 -1. And so I'm going to talk about that slide next time, that problem next time. This diagram here will show how you can actually calculate the charges on the atom. So here we'll try to calculate the plus and minus on HF, the plus and minus on HCl, and kind of compare them and see how they go relative to each other. But where I want to wrap up today is just a quick look at some Lewis structure rules. And so I just wanted to quickly try to see these rules, to start taking them in so we can have a chance to see these rules more than once to try to come up with Lewis structures. So we're trying to draw Lewis structures for larger molecules. And these will work for all the structures we've done so far today too. But what we want to do is start counting up valence electrons. We want to make sure we know how to do that. And so let's maybe start today with like CCl4 as a quick example of a Lewis structure, and maybe even like BCl3, a boron compound that can show us some comparison for like BCl3. And so if I'm counting up valence counts, hopefully, and this just like it's based on carbon's position, 4 for carbon, +7 for the chlorines, there's 4 chlorines. So this is 32 valence electrons for CCl4. Boron is next to carbon on the left side, only has 3 valence electrons, and then 3 times 7 for the 3 chlorines, so that's 24 valence electrons. And so then when I start to think of my Lewis structures, and these are rules also in the book, almost like the exact rules the book has, but we attach the atoms to their central atom. The central atom's the first atom. So the central atom is always going to be the first atom, then everything after it is attached to the first. So we have 4 chlorines on the carbon, and then I have 3 chlorines on the boron. Then I want to complete the octets of the non-central atoms. So what that means is I want to put lone pairs to fill the octets for everything except the central atom. And so I don't do, so for the octet rule, for carbon was good. For boron, you might think you want to put 2 electrons in here, but don't do anything on the boron. Just leave it be for now. And so then if there's any electrons left over that we haven't yet assigned, if I count the electrons used here, that's all 32, because I put 8 around each chlorine. There's 4 chlorines, there's none left over. And then I put 8 electrons around each chlorine, there's 4 of them. I put 24 electrons in this structure, there's no electrons left over. If I had leftover electrons, I would then put them onto boron, but I don't. And so then I want to think, should I make multiple bonds? And the answer is going to be no, because if I try to make a multiple bond here, that just doesn't work, because boron doesn't have a pull for those electrons in towards itself. If we leave it as it was, if I calculate the formal charges, we should have a 7 - 7 for the chlorines, and both of these compounds, 7 electrons on each of the chlorines, so they're all 0. The carbon was happy. It was a 0 here, 4 minus 4, just like CH4. And boron here is actually quite happy. It's 3 minus 3 for 0. So BCl3 is actually fine violating the octet rule. It's actually deficient of an octet, but this is a perfectly stable compound. Not the most stable compound in the world, but you can buy and ship this compound and it's stable enough to exist. And then if we try to do this, this doesn't work because it makes, if we make that structure there, chlorine goes positive. It would be 7 minus 6 for +1. Boron would be 3 minus 4 for -1. And that just doesn't make any sense that that would ever happen. So we'll talk more about why that doesn't happen next time, but I just wanted to see a couple quick molecules in terms of how we would apply more rules, and we'll see how we apply some of these rules as we continue along. All right, guys, have a great weekend.